We have currently two methods to take an alkene and change it into a vicinal diol, meaning two OHs on adjacent carbons. One way is osmium tetroxide and NMO in water, and what this does is adds two OHs syn to each other, so they're on the same side. The other method of adding two OHs is simply changing your alkene to an epoxide, and then opening that epoxide off in the presence of water in either an acid catalyst or base catalyst to give you the two OHs on adjacent carbons. And this results in an anti-relationship of the two OHs. So these two methods complement each other quite nicely. So the problems that you may come across is, first of all, the simple problems where you're given an alkene and the conditions. And then all you need to do is supply the product. In this case, we're going to draw the product as is without the double bond, and then where that double bond was, we can add two OH groups. And since osmium tetroxide adds syn, the OH groups, if one's a wedge, the other one's a wedge. Then I'm going to change the other substituent to a dash to match the trans relationship. So the syn relationship of the OH. This molecule itself is chiral, so it's racemic. We could have drawn it like this, or we could have drawn the product like so. Either of these two works. The relationship between this structure and this structure, well, 1, 2, 3, that one is R, 1, 2, 3, one is S, this one is R, this one, 1, 2, 3, a little harder to see, but this one is S. So this structure and this structure are the same structure. So you can do it either this way or this way. The important thing is the OHs are syn to each other. If we take the same one and add mcpba followed by base and water, predict the product. We can redraw the alkene as is, and we're going to draw in one OH because these conditions give an anti-relationship. So this OH is a wedge. The other OH must be a dash, and we turn this substituent to the wedge, like so. So this molecule is chiral. Start from a molecule that's achiral, so you get a racemic mixture of this. You can draw it like this, or you can draw the molecule. This is an OH, so the OH here goes on a dash, put a wedge there. Either of these two ways, these two are equivalent to each other. Okay, so that's one thing. One type of problem. Second type of problem that you might be asked to solve is I give you a starting alkene. And the product is a diol. You have to give me the conditions that go in this box. Now, since we have two ways of adding two OHs across a double bond, you need to redraw this molecule, the product, in either the syn configuration or the anti-configuration. If you draw it in the syn configuration, this OH is a line. Just rotate the molecule so that OH is also a line. You get this type of structure. You just need to fill in where these substituents go, the methyl and the ethyl. Well, if this OH goes to where this ethyl group was, the ethyl group goes to where the methyl group was, so that methyl group is a dash, and the methyl group goes to where the OH was, like this. And so the syn configuration if you reverse this process, the ethyl and the methyl group end up cis to each other, and this methyl group and that methyl group end up trans to each other. And that happens to match this structure right here. So in this case, syn configuration is what we needed to add. So the answer is osmium tetroxide, NMO, and water. Let's do another one. This time around, what we're going to do is we're just going to switch that oxygen from a wedge to a dash. Again, we need to figure out what we add to this. We redraw this structure in the syn configuration. OH there, OH there. So the OH went to where the ethyl group was. The ethyl group goes to where the methyl group was. Ethyl group becomes a wedge, and the methyl group goes to where that OH was. So this is the syn configuration. And if we backtrack to what alkene was added to, here the methyl groups are cis to each other, and the ethyl group is trans to that methyl group, so you get this configuration. And this does not match your initial starting material. So therefore, it's not a syn addition, it's an anti-addition. So the answer is mcpba followed by sodium hydroxide and H2O. You can double check this by redrawing this molecule in an anti-configuration. If you do so, add OH, goes to here, same one. We're going to change this OH into a line. That rotates this methyl group down into a wedge, and that ethyl group becomes a dash. This is the anti-configuration. And when we go figure out what alkene that came from, ethyl group and that methyl group are dashes, so they end up cis to each other. That methyl group and that methyl group, one's a wedge, one's a dash, so they end up trans to each other. And get this, and this matches our starting material here. Okay, so that's another type of problem where I give you a diol and an alkene, and you have to tell me what conditions were used to generate that diol. And your options are either going to be osmium tetroxide, NMO, and water, or mcpba followed by sodium hydroxide and water. Third type of problem. It's where I give you the conditions, and I give you the product. And you have to tell me what the starting material was. For that, you have to figure out the conditions and label them as either syn or anti. Osmium tetroxide, NMO, water, that's syn. So we have to take this molecule and redraw it so the two OHs are syn. So we want them to look like this. And when we do so, that OH goes to where that methyl group was. The methyl group goes to where that ethyl group was. And the ethyl group goes to where that OH was. This OH was already aligned in the correct position, so that stereocenter is fairly straightforward. And to go backwards, we have an alkene. Wedges go on the same side of the alkene, so this methyl group is a wedge, this ethyl group is a wedge, this ethyl group is a dash, and this hydrogen is a dash. And so you get this alkene, and this is what goes in the box. If we were to backtrack using mcpba and sodium hydroxide and water, and say we were given no, let's make this a wedge. This alkene here, sorry, this diol here, what we would need to do is redraw it so the two OHs look like this in the anti-configuration, because mcpba followed by sodium hydroxide water adds two OHs anti to each other. So this OH is aligned, matches up with the configuration there, so we'll just keep that one constant. This OH is a wedge, so we have to rotate it 60 degrees so it becomes in the plane. And when we do so, that swings this methyl group outward. It becomes a wedge. And then the hydrogen swings 60 degrees. It's still behind the plane. So we get this. And to backtrack to what alkene it came from, we have the double bond. The methyl group and the phenyl group are both wedges, so they end up cis to each other. And then this hydrogen and this hydrogen end up on the other side. So here is the product. This is the starting material.